Hello everyone, this is Professor He. Nice to see you again. The topic of this task is about the combined gas-vapor power cycles. Firstly, let's talk about the cyclic follies. Cyclic follies refers to the ratio of the thermal efficiency of a power cycle to the thermal efficiency of the Carnot cycle within the same temperature limits, which means the degree of follies of the cycle compared with the rectangular Carnot cycle in the temperature entropy diagram. Secondly, let's talk about the effects of working fluids on cyclic thermal efficiency. The working fluids have strong effects on thermal cycle efficiency. The main reason for the higher thermal efficiency of steam power cycle than gas turbine cycle is determined by the working fluid. The ideal power working fluid should have the following characteristics. 1. The critical temperature of the working fluid must be far beyond the maximum allowable temperature of the material. 2. The maximum pressure of the new steam saturation temperature T1 should be not too large, and the latent heat of vaporization should be as large as possible. 3. The triple point temperature should be lower than the atmospheric temperature. 4. The specific heat of liquid and constant pressure should be as small as possible. 5. In the TA's diagram, the saturated steam line should be as steep as possible. 6. The saturation pressure P2 corresponding to the condensation temperature T2 should be not too low. 7. Good chemical stability, non-toxic, non-corrosive, abundant sources, low prices, etc. The continued quest for higher thermal efficiencies has resulted in rather innovative modifications to conventional power plants. The binary vapor cycle discussed later is one such modification. A more popular modification involves a gas power cycle topping a vapor power cycle, which is called the combined gas-vapor cycle, or just the combined cycle. A sketch of the system and the TA's diagram for a combined gas-steam power plant are given in figures 1129 and 1130. The combined cycle of greatest interest is the gas turbine cycle topping a steam turbine cycle, which has a higher thermal efficiency than either of the cycles executed individually. Gas turbine cycles typically operate at considerably higher temperatures than steam cycles. The maximum fluid temperature at the turbine unit is about 620 degrees centigrade for modern steam power plants, but over 1425 degrees centigrade for gas turbine power plants. The use of higher temperatures in gas turbine is made possible by developments in cooling the turbine blades and cooling the blades with high temperature resistant materials such as ceramics. Because of the higher average temperature at which heat is supplied, gas turbine cycles have a greater potential for higher thermal efficiencies. However, the gas turbine cycles have one inherent disadvantage. The gas leaves the gas turbine at very high temperatures, which erases any potential gains in the thermal efficiency. The situation can be improved somewhat by using regeneration, but the improvement is limited. It makes engineering sense to take advantage of the very desirable characteristics of the gas turbine cycle at high temperatures and to use the high temperature exhaust gases as the energy source for the bottoming cycle, such as a steam power cycle. The result is a combined gas-steam cycle. A sketch of the system and the TS diagram of a combined gas-steam power plant are given in figures 1129 and 1130. In this cycle, energy is recovered from the exhaust gases by transferring it to the steam in a heat exchanger that serves as the boiler. In general, more than one gas turbine is needed to supply sufficient heat to the steam. Also, the steam cycle may involve regeneration as well as reheating. Energy for the reheating process can be supplied by burning some additional fuel in the oxygen-rich exhaust gases. Developments in gas turbine technology have made the combined gas-steam cycle economically very attractive. The combined cycle increases the efficiency without increasing the initial cost greatly. Consequently, many new power plants operate on combined cycles, and many more existing steam or gas turbine plants are being converted to combined cycle power plants. Thermal efficiencies well over 50% are reported as a result of conversion. Another improvement for a gas turbine is the steam injection between the combustion chamber and the turbine to cool the combustion gases to a safe temperature. The steam injection gas turbine cycle is to directly inject the steam generated in the waste heat boiler into the high temperature gas flowing out of the combustion chamber, and then the mixture of gas and steam enters into the turbine to expand for work, and in the waste heat boiler to release some of the heat back into the atmosphere. The water absorbs the heat from the turbine's exhaust in the waste heat boiler and turns it into steam, which is then injected into the hot gas Therefore, the steam injection gas turbine device cycle is a parallel dual medium cycle. Okay, that's all for this task. Thank you very much and see you next time.